What if you had a device which lets you log into your computer, not with a password, but with a physical key, like this? Well, let's build one. In this video, you will learn how to make a professional schematics for this project using the free software KiCad. We will also use KiCad to turn our schematics into a proper printed circuit board and have it produced for a few dollars. You can also use a breadboard. Then we'll learn another free software, Blender, in which we'll design a nice looking case that you can 3D print if you like. And all the hardware parts of this project will be in this single video. Let's get started. We will start this project by designing the schematics and we'll begin in just 30 seconds. First, a few words about our sponsor. PCBWay.com is a website where you can upload a KiCad schematic and have them produce a real PCB, a printed circuit board, just like the boards inside of your computer. Then you just solder on the components. The cool thing is it only costs around $5 and they ship all around the world. But more on this later. Our project is a very simplistic design in 3 modules, each consisting of just 1 chip each. There is an input module which contains a 74LS245 with 8 so-called tri-state buffers, where the inputs form an 8-bit secret key. Then there's the output module using a W65C51 UART chip, which transmits the secret key to the computer through the serial port. And in the middle there's the control module, where the main part is this on-off key switch that triggers the transmission. We also need to invert the signal, so we'll use a classical chip, the 74LS04, for that purpose. And that's all we need in order to make this device work. I call it the skeleton key. Alright you guys, so let's start by downloading KiCad. So just go to Google, search for KiCad, make sure that it's from KiCad.org and go to download and choose your system. So this is the interface and it's off screen now, but you go to the menu and you select new project. And I'm gonna call this the skeleton key. Alright, so there are a lot of different options here, but don't become frightened because of that, because we're only going to use a tiny part and it's going to be pretty simple. So first we're going to the schematic editor, which looks like this, and this is where you will spend the most of the time initially. This is where you create the schematics, and before you start, you need to change one option. So you go to the file menu and you go to the global settings, and then you can go to the schematic editor, and on the cursor you switch from small crosshairs to full window crosshairs and click OK, because this will make a lot of stuff much easier. And as you can see, you can scroll, and if you hold down your right mouse key, you can drive around like this. And down here you have some information that you can change if you go to the page settings. And this is the skeleton key. And that's all you need to add. Alright, so now we can start putting symbols on this thing. First of all, let's see how we're going to organize this. We have 3 different modules. So we're going to have an input module, an output module, and a control module. We can start by just adding text field. If I make this a little bit bigger and I click on this T here, control module, and let's make the text size 5, let's say. and then you just click where you want this to be. And I will make this smaller again. And it's still in the text mode here, so you need to press escape to go back to the other one. Let's change this to KiCad font and bold. Okay, that's better. Okay, so let's start by putting our key switch. So you go to the left menu here, you choose placed symbols. You can also press an A on the keyboard. And the first time you do this is going to calculate and find some stuff, but then you get to this view. And you can search for a lot of different things. You can have a transistor, for instance, and you get a lot of different transistors and so on. But we're gonna start with a simple switch push button. Here we are. So this is what we need. Something which can just lead power or don't lead power. So let's put this right here and scroll in a little bit. You press escape to go back to selection mode, and then you can just double click on this thing and you get a lot of options. The only thing which we usually change here is the value, and I'm gonna call this the key switch. Alright, so what do we want to connect to this thing? We need to have power, plus 5 volts on the one side. So we can start with that. And when you put power symbols, there's a specific thing for that, which looks like this. Place power symbol. So you click there, and I'm going to search for 5 volts. Just double click, and you can press R to rotate. And let's put it right here. And in order to make a connection, you can just click on this little circle here, and then you click once on the other side, and you have a connection. For some of these signals, it's also helpful to give them names, but I'm not going to do this with this right now. But with the output, I am. So let's see here. I want to connect this to a transistor. So let's create one of those. Let's search for, let's say, an NPN type transistor. There are 2 different types of transistors, and this is the one we're going to use. I want this signal to go into the middle leg, because a transistor works that way, that it leads power through here if there is power on the 3rd leg here. So this is like a switch. It's either on or off, depending if there's power here. So what we do with our switch will also turn on the transistor. And if we want to make a connection, but not connected to anything yet, you can just click, and then you click where you want it, and then you double click and press escape. So now we have a connection, and this one I want to name, because this will be our enable signal that we're going to use on different parts of the schematic. So we go to, let's see here, let me just, net labels, here it is. This creates a label for, well, a wire basically. And this is going to be our enable signal. Let's just call it EN like this. And then you can rotate it, and you see this little square. This should be on the label, on the wire, like this. And now this whole wire and whatever it connects to is connected to this label. So even if we place something in another module right here and don't put a physical connection, the system will still treat this as if it were connected to the other end, so to speak. That way we can make our schematics a little bit nicer looking and easier to follow and not have to connect everything all around the place. And I will not do this for every wire, but for some more important ones I will. Okay, so let's see here. When the key switch is in the on position, I also want to let it turn on an LED. So let's put an LED. So we press A, we search for LED, and we can take the first one. And I also want to have a resistor in between, so I'll put it up here, say. This I'm gonna name, this is the unlock LED. And if you want to move this thing, you click on it once and then you can move it. So let's put a resistor in between here. And for resistors, we just click R and we choose this, which only has the name R. And let's put it in between here. And for this signal, I want to use a 1K resistor, 1000 ohms. And we specify that by going to the value field and changing this R to 1K in this case. If we needed something which has 100 ohms, we usually type 100R for resistance. But if we have thousands or mega or something, we just use that. So 1K resistor, just to limit the current flowing through this LED, but still enough to be treated as a signal in the other end. So I want to connect something directly to this wire, but as you can see, it doesn't turn into this wire symbol. So we need to go to the right here and choose draw wire. And then you click, and let's go out a bit. And we click so it becomes like this, double click and press escape. So this will be our output, but we are also, let's see here. Right, so this part, because I need to be able to treat this signal as both an on state and an inverted state, because at one point we need to have a digital 1 being sent when the key switch is on, but on this end we need to send the different signals. So if it's on, it should be 0, and if it's 0, it should be 1. So we need to put this in through an inverter. Let's move this wire. Let's see. We need to do it like this. Alright, so how do we invert this thing? We need to use a chip. And so we press A, and the chip's name is 74LS04. And this is an inverter, as you can see. But it's not just one inverter, it's a chip which contains several. So what we need to do is we need to right click on it and click on B. No, that's not right. It's an easier way. Let's do it like this. We press A, 74LS04, and then we click here and we put this one, and then we keep clicking, because we need to, if we don't place all of these, we will not be able to place the actual chip, which is this. So let's do something like this, and now we can delete those other ones, I think. So let's delete all of these but one. And then we can move this chip up here. So one of the ends we need to connect to ground, and one of the ends we need to connect to 5 volts. So let's see what's best here. I want to put these quite close together so we know that they are part of the same chip. And then let's connect this VC. We can do like this. We can copy this symbol, Control C, Control V, and we can put it here, and we connect it, and we can select. It's a bit tricky when I put them too close together. Let's see. Need to have this as well. Here we go. All right. So let's do something like this. It's not perfectly symmetrical, but it'll do. So we need to have a ground symbol as well. And since we know that this is 5 volts, I don't need to have it shown on every step. So let's unclick like this. And let's go to place power symbol. We search for ground. And I like the one which is called ground ref here, which looks like this. So let's put it right here. And let's double click, change the value to just ground, and unclick show. And we connect. Alright, and let's click on this so we can drag it out, and to make this is a good use case for the big crosshairs. So okay, the grid is not right. Oh yes, it is. It shows a little bit weird sometimes. But okay, so we push the enable signal through this one, and then on the other end we are going to have the inverted enable. So let's place a label for that as well. By using the net label thing, and let's call this, I'm gonna call this ENB, where B stands for bar. So an EN with a bar on top, which means it's inverted. But you can have a different name for it if you want. So I'm gonna put this right here, like so. Alright, it's starting to take 4. Oh, this is wrong. This should be, let's Control C. What did I say? ENB. It should be here, of course. Alright, so this is almost the whole control module. Let's say we have all the outputs, because this is an output, right? Let's say we have all the outputs on the right and left, on the right side. So what we can do is we drag a wire over here, let's move this label. It's not fond of moving labels, so let's delete this label. And let's recreate the EM, and this is going to be here. Alright, so now we have the two outputs, the enable and the inverted enable. But we also need to make this so it has a default state. Because if this thing is not connected, by the way, we should connect the other side of this as well. Let's do it like this. We copy this. Let's see, we want to connect this and to 5 volts because we want current to flow through here if this is connected. So let's just drag a wire and we go here, click, and we go here and click, like this. Okay. But we need to have a default state, because if this switch right here doesn't give any power, in that case there will be no circulation of current here, which means that these will not be 1 or 0. So we need to connect this side to ground as a default state. So I'm gonna take this resistor, copy, paste. I am going to let's just put it here, connect it like this, and then we have a ground symbol. Like this. And this is going to be a bigger resistor, so this is going to be 10K. So if this switch is off, the current is going to become 0 from connected to this ground through the 10K resistor. But if this switch is in the on state, it will activate this transistor, which will put 5 volts through to these signals instead of this ground thing. So this is a so-called it is called a pull-down resistor. That's the one, because it sets the default state to ground. And this is our control thing. But in addition to this, I also want to have a second LED which just indicates that it is power to this circuit. So let's see how we are going to do that. Because this one we want always to light up. So maybe we could just let's copy these two and we can paste them down here. We need to reorder them though, so let's delete this cable here. Like this. So I want to move, I want to rotate this. And this is not unlock, I'm going to call this how. And this should be connected directly to 5 volts through this resistor. To ground, which should make this always light up. So this is always lighting up, and the other one is only lighting up when this is on the on state. Okay, a lot of moving parts, but I hope you understand it all. So let's move this so it's a little bit centered in this control thing, and let's add some framing around it. Let's do one of these. You click once and then you click once, like so. And let's make this solid, and let's give it a color of maybe some dark blue thing. With a little bit of shine through. And a little bit fatter. So what about 5? No, that's a little bit too much. Let's say 3. Still too much. 2. Let's say 1. Okay, so our control module is done. Quite nice looking sketch, don't you think? Yeah, I think so. Okay, so what's next? Next we need to take care of the input. So we can copy this thing. We can put it somewhere here. Maybe we can have it like this. And then we have the control here, and maybe under there we can have the last one. Okay. And this should not be control, this is the input module. And the input module is really simple. All it is one chip, a couple of connections, and a couple of resistors. So first we need to take care of the chip. And the chip is called, let's see here, this one. 74LS245, and this is a tri-state buffer, and I'm going to show you on the blackboard how it works. But the problem is there are a lot of different things you can choose from in this program, a lot of different chips and stuff, but not everything is here. So this chip does not exist in KiCad. So we need to create it from scratch. And how do we do this? Well, we can save and click this down, and we go to the symbol editor. And then we go to the menu and choose new library. And you can choose if this is going to be your global library connected to your machine, or if it's going to be part of the project. I'm going to choose that. And then you give it a name. I'm just going to call this library, because I'm only going to have one of these libraries. So each library can contain multiple chips. Okay, so then you right click on library here and hit new symbol, and you give it a name. So this is the 74LS245, and you can just click OK here. Alright, so how do we want to do this? What's important here is that we get all the different pins right. So let's see here. I want to see if I can change the grid. It's a little bit different on my Windows machine, that's why I don't find it, but let's not care about that right now. Let's look at this datasheet, and I'm gonna link all the datasheets in the video description. So as we can see, we have 8 of these inputs called A1 to A8. We have a ground and we have a 5 volt. And then we have a direction which selects if it's going this way or this way. And then we only have one important thing, which is this enable signal here. And as you can see, there is a small bar on top of the enable, so it's an active low, which means that we need to put in the ground directly connected to this, and that means that this chip is activated. So that's what we need to do. But let's create all of these pins. So we have 8, 9, 10. So on the right here, we choose this symbol, which creates a pin. So let's start with the VCC, which is the plus 5 volt input. And by the way, maybe we should start with the one that they call 1. So let's see, it goes from this. So the direction pin is the first. Let's start there. So direction, the pin number is 1. And this is an input. And we can put the rest as is for now. Maybe we could, no, let's do it like this. And we click OK, and we put this anywhere really, because we're gonna organize it later on. Let's just put it here, and let's move this symbol identifier away for now. Okay, So it's going to take quite time to add all of these manually. So when we have one, we can click this little table here, and we get a table. And this is easier to work with. And let's see, we have 20 different. So let's just click this plus here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. And now you just go through and add one per each. And don't forget to change the pin numbers. I'm going to fast forward. Okay, welcome back. So now I have added all these pins according to the datasheet. I did name this one EB for E bar to follow the same standard as I have done before. And we need to change the electrical types because all of these are not inputs. The A1 to A7 are inputs, but let's see here. The ground should be changed to power input. And all of these, let's see, is it possible to, yeah, you can select all of these B types and change them to output. Okay, that didn't take. Why can I select multiple if I can change multiple? That's a little bit annoying, but all right, let's do this the inconvenient way. All right, so all the B pins are outputs. The enable is also an input, but we're going to change this symbol to inverted. And the VCC is a power input. So this should be a power output, right? Okay. Let's also let me see how it looks. So now we have all of these different pins, and we want to group them like it's done on the datasheet. So from direction to ground should be on the one side, on the left side, because I'm gonna tilt this. So direction all the way to ground. Let's put them here. And these we can put here. And by convention, when designing these things, usually you do the VCC and move it up, and you do the ground and you move it down. So we can double click this and we change it to up position like this. So the dot right here is on the down side. No, let's do it the other way. This is the correct thing. And we do the reverse with this one. So this should go down like so. No. It looks weird. Yeah, I was right the first time. This should be up. Annoying. No. This should be the other side. Right, so all the labels are on the inside. So we need to change these ones. Isn't there a way to change multiple at the same time? Yeah, I think it is. If we go to the menu to the left here, and we say orientation, left. Ah, there we go. You learn something every day, or what do they say? Okay, so now we have the general part of this. Let's also see, where did we put that U label? It disappeared in everything here. So where is it? Ah, it's back here. Let's grab this, put it on the outside, and put this back. So now we want to draw a box. So we take this box icon, and we want to have the end of it covering, going through these pins right here. So let's align like this. Escape. We double click. We change it to fill with background color. And now we get this nice looking KiCad kind of thing. So let's save. All right, what else? I think we have done all of these right here. Let's take this label and put it in the corner somewhere, maybe here. Let's see. Okay, so now we have one of these. We can close this down and go back to the schematic editor. And now we can place this. So we just type A, search for 74LS245, and now it's in here. Let's just double click and let's put it in, let's see, we can have it in this direction, like so. And how are we going to connect this thing? Well, what's this in the middle right here? That looks really weird. But this brings me to one other important thing. We can actually, wait a second, this is not the one we did, right? LS 74LS245. It should be the one in the library. This is the one. Okay. That's better. Okay, so let's connect the power and ground, and we can just copy these from here. So we click on this and on this with a shift, and we Control C. Go over here, Control V. Take this thing and put it on top. Rotate. And it should align with this. We connect. And same with this. So So we have power and we have ground. Before I forget, let's go to the control thing, and we need to specify that this plus 5 volt grid is a power input. So let's go to place power symbol and we search for flag and this power flag right here. So what we do is we connect this to the 5 volt grid, and this will just tell the system that this is one of the power inputs. All right. Okay, so let's see how we're going to do this. The enable bar signal right here should be connected to the, let's see, it's going to be connected to this ENB right here, which actually means that we don't need to have this, or do we? Maybe for the direction pin, is that it? So let's see here, if we go to the datasheet and check for the direction. So how does that work? Direction, and we want to go from bus A to bus B, which means that the direction should be high. Okay, so that means that we want to, well, we can actually connect this to plus 5. So let's take this one and we place the one here, connect, and the enable we can drag out a bit, double click, and we select this. In our list here we can choose the enable bar and we connect it like so. So this ENB right here will be connected to our ENB right here. But maybe we don't need this enable signal. So let's delete it for now. And let's just connect this to ground instead. So click and click and click. So something like this. Okay, and then we have the outputs, the B1 to B8. So these are going to be connected to another chip. So let's just drag out box. Let's see. Let's drag out boxes like this. Click, double click, click, double click, and so on. And now we need to select the grid names for these, and I'm gonna call these data B1. And then we can just click again, data B. Let's copy this to we just go through all of these. Then we have B4. Actually, I want to have this starting at 0. So let's change this to B0. And we move this. If we press M on the keyboard, we can move it as we want. So let's put it here for now. And then we select all of these. And M, and we just move our mouse one step down, click, M, like so. So it doesn't add up with these right here, but I have the strategy that this inside of here should align with a datasheet, and these should align with what bit they act as. Because these 8 bits from B0 to B7 will become a byte, which is being sent over to the computer. Alright, so these are our outputs. By the way, maybe we can move these in a bit so it looks a little bit nicer. Something like this. All right. And what about the inputs? Well, we're going to have a secret key. So an 8-bit secret key. And in my case, let me just create one of these text boxes. In my case, I want to use 0100 0001. But you should make up your own, because this is the secret key that is going to be transmitted to the computer when you turn the key. And it needs to be something that you pick. So this is what we want to do. And how do we do this? Well, we have these 8 bits on the input side, and every 0 we connect to ground, and every 1 we connect to +5, right? So one way we can do this is if we zoom in a little bit here and delete this cable, and we move this symbol away a little bit. So let's start with the ones. So the first bit, which is our A1 right here, that is going to be a 1, and the second to last should also be a 1. So the A1 and A7. So let's click A1 and take it out a little bit. Click, go up here, use the crosshairs, click, click, and we will also connect the direction, because that is going to be connected to +5. So we connect these together, we move this and connect it like so. And the rest of these should be connected to ground. So we do the same thing with these. And don't worry about crossing cables now, because that's not a problem at this stage. So what we are going to do is we are going to go out just like this, connect, click, connect, click, click, click. We connect this as well, and we connect this one like so. We take the ground symbol, we make a copy, we can let's do it like this, and then we connect it like so. It's a little bit tricky to see, but still I think it's quite okay. Maybe like this, just to emphasize, I mean the other way around, just to emphasize that these inner are connected to this and the outer connected to this. So this will form our key, and when this enable bar signal goes to a logical 0, these bits will be sent through the chip to these outputs right here. And that's all that this module is going to do. So let's see, can we rotate this? Yes, we can. And maybe make it a tiny bit bigger. And just do something like this to indicate that secret key. And let's take this box, copy, paste around here, use the crosshairs to align, and do something like this. Maybe we can take all of this and try to center it. All right, pretty nice. So all that is left is our output module. Which is going to be the most complicated in one way, but in another it's not. Because we're only going to use one chip and connect it to different. By the way, I forgot one thing, didn't I? These outputs right here, they need to go through resistors. Because we need to have a default state, since this is not transmitting anything when it's not enabled. So we need to have a default state of each and every one of these bits. So how do we do that in an easy enough kind of way? I think we need to delete these connections right here. Just the connections, not the labels. And let's move these out a bit, try to keep them aligned. Let's see if we go here. Something like this. And let's grab one of these 10K resistors, because this is going to be a default state. We paste, we rotate, and we make sure to align it with the individual bits. And let's copy this and make a few of these. By the way, before we do many of them, we need to change these so we can put it like this. Let's see if this looks good. Yeah, it's kind of okay. So you just keep copying these down like this. Alright, so now you just follow the same steps and finish the rest of the modules. You can follow the schematics PDF, which I will link in the video description. I'm going to fast forward a little bit so this video will not be 10 hours long, but if you want to follow it step by step, I'm going to put the full uncut section of this video by the end of the video. But for now, we will go to the next part. Alright you guys, welcome back. So we're gonna start building the PCB, the printed circuit board. But before we can begin, we need to configure KiCad based on the supplier that we're gonna use. Because each supplier has their own machinery, and we need to make KiCad compatible with that. So what you do is you can Google for capabilities, and then you select one of the PCB factories. So in my case, PCBWay. And if you want to use PCBWay, please use the link that I have in the description, because then you support the channel and you will get 10% off. But you go into the capabilities, and all the sites have something similar to this. And here you can see how big holes can be, and thickness of different stuff, and a lot of different things. But instead of entering all of this manually, which you can do, you can use a template. And this is not my template, but this is the one that I use. So this link is also in the video description, and here you can see the different websites, the different factories. And if we go into PCBWay, for instance, we have this PCBWay file right here, and this we can use to configure all the machinery. So let's go into KiCad, and we can start in the schematics editor, and you go into the preferences, the settings. So let's see. Or actually, I think it is in the, let's see here. I think you need to go into the PCB editor, and inside of here there is board setup. So you go to the file menu and board setup. So here are the design rules. You see there are a lot of different things here, and predefined sizes, a lot of stuff. But you can use this button right here, import settings from another board. So you click this, and then you select the file right here, and you make sure that everything is selected, and you click import, and then everything will be configured for that stuff. And let me do that actually. So because I have already done it before, but I'm not sure if you need to do it for each project, since it's called board setup, so it seems pretty localized. So let's see. I think you only need this file. So let's try this. I really do not like GitHub. There's always a lot of problems with it. So let's see here. I guess you need to go to code and download zip. And unpack. And now, if we import from another board, we go to Downloads, KiCad, PCBWay, and we select this. And open, select all, import settings, OK. And now everything is configured for this. Alright, so how do we do this? Well, the idea with this PCB part of the program is that you put all your components here, you can import them, and then you organize them in some good way, and you draw wires between everything. Because that's what a printed circuit board is. It's a lot of holes with pads that you can connect stuff to, soldering the components, and there's a lot of so-called tracks. So a track is like a wire, but it's like a two-dimensional thing on top of the board or on the bottom of the board, which leads power, electricity, current. Alright, so the first thing we do is we use this green button up here, update PCB from schematic. Then we get this screen, and we can keep this default settings, and we click update PCB and close, and then we get this little view right here with all our components, and we can just click somewhere here and drop it. So now we have all of our components like this, but it's not it's not in the correct order. It's not. It's just sorted somehow. So what we need to do is we need to organize this a little bit better. So if we scroll in like this, we see all of those tiny lines here. So if I click on this component and move it, you see that from these pads there's lines drawn. This is called the rat's nest, and this tells us how it's supposed to be connected. So we need, and one thing is very important, we cannot crosswire, because the tracks are a two-dimensional thing. The electrons are just walking around on top of the board. So we cannot cross them, but we can use both sides, both the upside and the downside. So I'm going to show you how you can think. But first off, we want to sort the stuff so it looks something similar to what we have here. So these should be close to this chip and these connectors and so on. So we need to group everything. And I'm starting to feel happy about the general organization of this. So what we need to do is we need to tell the system where the edges of our board is. So we do that by first changing this grid here to 1 millimeter, and then we choose edge cuts. So that's used for this. These are different layers used for different things. And the edge cuts, the only usage is where should they cut the board. So you just draw a rectangle. So let's click somewhere, and I want to make room for holes, mounting holes as well. Maybe we should add that first, actually. So let's save this. And if we go back to the schematics editor, we are going to add, we can have extra stuff here. So let's create another label, another box. Something like this. So how do we add holes? Well, we press A as usual, and we can search for hole, and we have this mounting hole right here. So we add it like this, and we don't need to position it on the edges. We can have it wherever. This is not looking too nice. Let's make this a little bit smaller. And this shouldn't be called input. This should be something like this. Okay, so let's double click this mounting hole, and we need to select a footprint. So we can click this, and we will see only the mounting holes. And I would like pretty big mounting holes. So let's see here. Maybe this one. So let's check 3D viewer. Let's do option 3 and move this away. Okay, it's just a regular hole. That's perfect. So we press OK, and then we copy and paste this. This, and then we hit save, and we go back to the PCB editor, and now we click this green button up here again, and now it's going to update the PCB, and we will get these holes like this. So now we can move these where we want them, so where we approximately want them, and use this right here. So let's see, I don't like leaving this much room. Could we move this somewhere? Where do we have here? Unconnected. sure, but maybe we could put them something like this instead. And if we take this and move and we rotate like so, and we take these and it's a little bit difficult to select the right things sometimes. So let's see. What if we were to move this something like this? Because we want to use as we want to make this as small as we can, but still we want to fit everything. Maybe here. Let's move these over a little bit. And same with this chip. Something like this, I think, would work. Maybe we can move these two. Maybe we can move it down just a hair. And make sure to align everything. Something like this. That's good. Alright, so let's put the edge cuts. Make sure you have selected the edge cuts here. And then you take this rectangle thing here, and we can go pretty close. So let's see. I need to move these up a little bit. Maybe something like this. Okay. So make a little extra space, but not too much. Something like this, I think. Right. And then I want to round these off a little bit. Still doesn't look quite right. And maybe we don't need to have this mounting hole label here. So I want to have it as evenly distributed as possible. And now we want to round these corners off. So what we can do is we take this arc tool right here, and we can click in the middle of this hole. Click once. And you do this. And you scroll in a little bit, you click here, and you take this and you drag it down. Ah, my bad. Let's remove this. And let's, instead of using this rectangle, let's draw lines. And let's start where these intersect. And we go down. Here. And we go there. Double click, escape. Okay, so as we can see, now we have this rounded corner here. And if we go over to this side and we draw an arc, so click in the middle. Let's do it again. So click, click. Okay. So we should move these in a little bit. So let's take this and move it one click, like so. And draw an arc, click, click, click. And now we take this little edge here, move it in, and we take this little edge, move it in. And then we do the same for this thing right down here. Alright you guys, it's starting to look kind of nice, so let's do option 3. So this is how it looks currently. Quite nice, huh? And you see the rounded corners, and you see our chips, and they have the correct size, correct number of legs. Here we have all our resistors. the key will be here, and we have our two LEDs. And here is our crystal. We'll have the key right here, and here is a transistor. Everything looks as it is supposed to, I think. But we need to add some stuff that I forgot about. For instance, power. How do we power up this thing? So I need to add, let's see, this is the power input. Maybe we can rotate this. So let's see here. No, we can keep it as is, but let's draw an additional connection here, which will be the power input. So let's add some, I want to have holes that I can use and connectors. So depending on what cable I'm going to use, I want to have options. So let's see what connectors we have here. So 1 times 2. I think this is what we need. So let's put it in this direction. No, wait a second. Maybe like this. We want to align it with this. So let's say this is our power input. So let's see what we can do with this thing. Value. Can we change these 1 and 2? Show pin names. But where does it get the name from? Let's try. If we set show pin names. Okay, what does it say? Pin, can't see. Let's move these out of the way. Pin 1 and pin 2. So now this pin is selected. What can we do? Assign net class. Okay, so maybe that's it. Let's see what happens. If we just connect this right here, still doesn't. What if we add something which we call 1 and we put something here? No. What if we call this pin 1? Underscore 1. Oh wait, pin functions here. Alright, so let's say, wait a second, I need to connect my mouse, I ran out of batteries. Alright, so let's say pin 1 is why can't I change anything? There must be some way to change this, right? It's not always easy to understand this program, right? Well, let's remove both pin names and pin numbers. And let's add texts here manually. So let's say we have a plus. And a minus. Something like this. And I also want to have one of the, by the way, we don't need to show this. But I also want to have pads, so we can connect if we have a cable with a stick at the end, so to speak. So where can we find these? If we scroll down on the sorry, on the connections, or if we just search for pad, lead pad. Ah, wait a second, if we search for hole, mounting hole with a pad, perfect. So, let's see how we're gonna connect this thing. Maybe we can just do something like this. paste. And this should be connected to ground. Alright, so something like this. Now we have the ability to connect an external power source, either through these pins or through these holes. By the way, we need to choose a footprint, I suppose. And let's make it Let's make it 2.5. Same for this. And what about this thing? So, what kind of connector? Pin header, 2.54. And it's supposed to be vertical, I guess. And it should be two of them, so this. And let's double check. Yeah, that's what I want. Okay. We could get power from the computer, but most of the time nowadays a serial connection on a laptop does not provide enough voltage. So I don't think I want to support that. However, what we totally forgot about inside of the output module is a way to communicate with the computer, because we don't have any serial port. So that we most definitely need, and it's going to connect to the to the TXD, this one. So let's put it down here, and I'm gonna search for I think it's called DB9. Pins, mounting holes, socket. It's a socket, I think. Quite big thing, this, eh? Let's put it down here for now, and let's move this around a little bit. Maybe it's enough if we just move this whole thing up like this. And we missed something. Hope that was the only thing. Okay, so let's see here. We need a footprint. Socket vertical, and let's see, vertical. No, we should have it horizontal, right? Socket. Edge mount. Well, I think this is what we need. Let's double check. No. What about this? What about this one? This looks more like it. Yeah, but it's the wrong connector, I think. I want a mail. Let's make this a little bit bigger. Does it say if it's a male or a female? It's gotta be one of these D sub 9s. And it's gotta be horizontal. But I would prefer if we had a male connector. Oh, wait a second. Now we're talking. How is it connected? Like this. Well, let's run with this one. Okay, so how do we connect this thing? I know that ground is supposed to be on the on number 5 here. Since we have a ground connection here, why not reuse it? But then we need to connect one more of these. So let's do a quick Googling. DB9 serial pinout. Let's see. A computer's COM port DTE is usually male. Really? So maybe we should change it to a female then. So the computer is the DTE. So we are the DCE. I would like well, these two are switched. So on the computer, receive is on 2, transmit on 3. That means that we are going to connect ours to port number 2. Okay, so 2 should be connected. Not very elegant, but it'll do the job. And this is all we need to connect. So let's add some not connect labels so our program will not freak out. And where do we have that? Here. So 5 we used, but not these. Alright, and while we're at it, let's also double check that we have gotten all of this correct, because I think there is 1 or possibly 2 that we need to modify. So let's see. Let's double check the datasheet for this thing. And I'm looking for here. So reset input clock. System 52 clock and clocks all data transfers between the system microprocessor and the ACIA. Okay. So let's connect Phi2 to our clock circuitry. this. We're going to drag a very ugly connection. So let's see, where do we want to connect this? I think there. Okay. What else? Read write. That we have taken care of. Interrupt we're not going to use. Select, register select. These are also okay. The RTSB output pin controls the modem from the processor. The state of the RTSB pin is determined by the contents of the command register. Okay, so we don't need to care about that. The enable state is with CTSB low. The transmitter is automatically disabled if CTSB is high. Okay, so we should tie CTSB to ground. It's this one. And we do have a ground connection here, so if we just move this down a bit, we can do this. Okay, what else? Indicates ACIE is enabled. A high indicates it is disabled. Okay, so this is an output. Indicates to the ACIE status of the modem. A low indicates the ready state and a high not ready. So the SRB should be low. That's this. Okay, and I think that's it, right? Low indicates that the modem carrier signal is present, and a high that it's not. So maybe we should tie DCDB to low as well then. DCDB, that's this. And that's all of it. Okay, we are starting to see the end of this, I think. Yeah, so let's go back to the PCB and let's update with this green button. Update PCB, close. And now we have some new stuff that we want to try to find a place for. And this looks really big. But most of this should be outside, or at least some of it should be outside, but not all. So how do we take care of this? It's gonna stem from this right here. These ports. So maybe we could just expand this a little bit. So let's see how we do this. We need to select this and this and this, as well as this and this. press move. Try as best as we can to keep it aligned. Let's take this thing, rotate. Maybe we should leave some room here because we need to worry about the connections. So let's take care of these again. And move. So we want to have the border here. Something like this, and then we just connect these again. How does that part of the circuitry look? It's quite a big thing, this connector, but this looks perfect, I think. So now we only need to figure out these. We'll be right back after. Alright you guys, welcome back. So now I have made this look nice and everything fits. I also placed out these power things, and I added some labels like unlocked and 10K resistors and so on. And when you do, make sure to click forward tilt screen. Otherwise it's not going to be printed. Alright, so if we do option 3, this is how it looks. Quite beautiful, no? With all the labels and all the different components and everything. I think it looks pretty nice. Let's see how big this thing is. So what we can do is, if I make this a little bit bigger, you see this ruler right here. So go here and make sure that it's in the right angle. So let's see, it's 82 by let's do this. By 74. So 82 by 74. Let's write that down. 72 by 84 millimeters. Okay, so it's less than a decimeter in each direction. I think this is going to be pretty cool. Alright, so now we are done with the PCB. So we need to export it in a format that the machines in the factory can understand. And that format is called Gerber. So I'm going to go into the directory right here and create a folder. if I am able to click here, yes. And I'm gonna call this Gerbers. So these files are called Gerbers or Gerber files. And it's quite simple actually to do this. All we need to do is you go to the menu. It's off screen now, but in the file you can select export. No, you choose plot, P-L-O-T, plot. And then you get to a very complicated, by the way, before you do, you need to run the diagnostics so we see if there are any errors. And actually, before we do any of that, we need to connect everything. Would have been fun if I forgot about that, the most important, crucial part. Alright, so now we are going to connect everything. And the good thing is we can make the connections on the front and on the back. So it makes stuff a little bit easier since we cannot do any cross wiring. So let's see where we start. Let's start where the signal comes in. And I'm gonna wait with all the power pins and power connections because those would need to be wider. But up here where you see, maybe I need to make this a little bit smaller. You see this track right here. This should be 0.2 millimeters, and that's what we are going to use for the signal wires. We're going to use bigger cables for the power cables, and then we select front. That's important. All right, so where does everything begin? Well, everything comes from our tri-state buffers, right? So the signal, if we look at the other sketch, and we go to the input module. So this is where the signal comes in, right? This is our secret key, and this is where the signal comes in, and then it goes out on the other end here. So if we zoom in on this thing here, we see that here are all the data pins. So that's the output. The input is this. So you see most of these are ground, as you might remember, because we connect the logical zeros to ground and we connect the logical ones to +5. But we can't do this yet because we have not let's see here. Well, these are signals. These are not power per se. So we can actually do this. So that means that it's going to come from here. So since we're going to have a bigger cable between these two, the connection that we are interested in is the connection from +5 here and over to this and this. So let's start in that end. So what we do is we go to this route single track, or press X. Alright, so we want to start at this +5, so we click, and as you can see, it draws a red wire here, or a red track, and red means the front side. And you see that these light up, this and this lights up, and that tells us that we should go that way, so to speak. What about this? This should go there, but not a big one. And then we should have +5, so we can extend our backbone connection. To there. And what else do we have here? We have these, right? But they are supposed to be not connected. Didn't I specify that on the sketch? No, because we deleted those. Is it possible to specify it here directly? So let's see here. Maybe it's no problem. We'll see when we run the diagnostics. It might complain about that. But I think we got it all. So if we were to look, it looks like this, pretty clean. And on the other side, we have most of these. But it looks like a proper circuit board, no? And I believe everything is connected the way it is supposed to be. Alright, so let's run this diagnostic and see what happens. So we go to this, I think, design rules checker. Run DRC. Okay, we have some errors and some warnings. Let's start with errors. Clearance violation. Net class D4 clearance. Clearance. .1. Actual 0.1 millimeters. So what did it select? This pad right here. I think maybe it's this space right here. So in order to fix that, we need to go to the main screen and the footprint editor, and we try to find our footprints in this. And we need to have a little bit more space here. So maybe if we change the pad size to 3.5 instead. And same with this one. Something like this, because I don't want to change the whole size. And we save. And then we can go back here and we need to update. Did it take? Let's see. Update footprints. Okay, so now we have the space. Let's see if this fixes it. So let's go to the rules checker. And now we have 3 errors. So this was the right thing. Good. What about this? Front solder mask aperture bridges items with different nets. Front solder mask bridges items with different nets. Rear solder mask bridges items with different nets. What is it? What does it mean, bridges? I've never seen that before. Because this pad goes from +5 to +5. It's not bridging nothing. And solder mask. Is that these? Does it have to do something with a name right here? Let's just try, but I don't think so. Yeah, maybe it was that. Clearance violation. And where are we? Ground on back. Pad 8 unconnected of U3. Clearance violation. Okay, so it's colliding, is that it? Let's see if this was the problem. that it was too close, perhaps. Yeah, I think that was it. What about this? Missing connection. Oh, I think I delete. No. Where are we? I'm not sure what it's talking about. Net U3 fee 2. U3 fee 2. Okay, so this chip is U and fee. Is one of the connections to the clock circuitry, if I remember correctly. So maybe this. Maybe we should have a connection between those, or no? U3 fee 2, it's this one. So this should be connected somewhere. Which was it? So let's see here. XLT. Fee 2, okay, this one. So let's see where this should go. Okay, so this should be connected to that. So let's see how we do that. This one, and there we have a connection already, but it needs to go here. So this is the thing. Okay, but this should not be that big. All right, so let's run this DRC again. 0 errors, nice. Alright, so the time has come to finally submit this thing. So we're gonna do one last thing. You click on forward silk screen and on text, and then you type in the text way. And this is for PCBWay. The other sites have something similar, but not exactly the same. Because if you do this, and you put this somewhere, let's say, I don't know, up here maybe, then, because they're always going to give this some kind of a production number. And if you don't put this label, they are going to print that production number. They are going to decide where to print it. But if you put this text here, then you can use a special option inside of the web interface where you can decide that this should be replaced with the part number. Alright, so let's save, and I have already created an empty file for the Gerber files. So we go to File and Plot, and then we get to this screen, and there's a lot of stuff here, but you don't have to worry about most of them. One thing is very important though. You need to remove this use extended x2 formats, because that is not supported. So let's see, the rest is okay. And now you click this, generate drill files. And you select an output folder, which is my Gerbers. And you can say yes. And this should be, let's see, this should be Gerber. And this you don't need to change. And make sure that you generate map as well, and that it's in Gerber. And then you click generate, and it makes a lot of files, and you click close, and then you click on plot. Let's see, should we remove any of these? So we have the front and the back, forward paste, forward mask, silk screen. Yeah, then you click plot, and close. Alright, so now that's done. You can save and close down this one and this, and now we just want to verify that it looks alright. So we go to the Gerber viewer, and it looks like this, and then we need to load our file. So we open project, Gerbers. Let's see. No. Let me just see here. Open this, open Gerber plot files. We go to the Gerbers and we select Maybe it's this one. Open auto detected files. So Gerbers, and let's see which one's the main one. Is it this? No. There are so many files. Search map. So these are the different layers. Maybe we can just pick any of these. No. Okay, so now we open the back. So let's open all of them then. It's hard to move this window. So let's see, we go to the Gerbers, we select all, and one of them I have already selected, which was the back, so let's remove that and open. Okay, so there we go. And then we see the sketch, which should look pretty similar to what we had already. And if we do Alt 3, I think we can do that. Oh, maybe we can't here. But as we can see, everything looks okay. So now we can close down KiCad. So close this project and close program, and then we go to this directory and the Gerbers, and we create the zip file. So on Mac you just compress, on Windows you select create zip file or something. So now we have this gerbers.zip. So now we go to the link which is connected to me and the offer. You get $5 off your first order, and you support my channel. Okay, so you come to this screen, and if you remember, I saved here that this is the size of it, 72 by 84 millimeters. So we say 72 by 84. Did I get that right? 72, 84. And you choose a number, and number of layers should be 2 because we have a front and a back, and the thickness for a 2-layer circuit board, the default option of 1.6 is good. So we click quote now, and now you will get a lot of different options, but you can leave most of them as default. So board type should be single pieces, and this you don't do anything with, and this we have already chosen. Layers, same. Here you can choose the material. The default is good, and it's the most cheap of the ones. And here you don't need to change anything. Here we have the thickness we have already chosen. This don't need to change. And then solder mask. This is the color of the board. So you can pick any of these. And I'm thinking matte green maybe. And the silk screen, that is the color of the text on top of the board. And black is, let's see, white is the default. And I'm going to keep it as white. And this you don't need to worry about. Surface finish. This is important because this default option, hazel with lead, is not permitted in all countries. So I would say hazel lead free, because this is almost as cheap as this one and it works fine. But if you want to go big, you can have gold or whatever here, but this is okay. And this you don't need to change. And this is how much copper you want on it. 1 oz is fine. And here is the remove product number. So the default is no, and you can pay extra to remove it, but specify a location. That's what I was talking about before, the way. So this doesn't cost any extra. And if you have any special requests, you can type it in here, and you will get the board sent to you. But if you're not good at soldering, you can click here for the assemble service, and they will assemble everything and solder it for you and all of that. I don't know how much this costs though. But I want to solder myself, so that means everything is okay, and we click calculate. And as we can see, the let's see here. Okay, apparently this matte green was quite expensive. I'm not sure why. So I picked the regular green and now it went from $50 to $5. And then you select your country, and this is so it can calculate the shipping. In my case, it's Sweden. And then you have a lot of different shipping options, depending on how fast you want to get it. But if you are not in a hurry, you can pick this option, 6 to 10 business day, and then in my case the total cost is less than $10 for 5 copies of this board. So it's not a lot. And then of course you can pay more if you wish to do that. I, however, want to have a little bit faster, I think. So let's see what we have here. 4 to 6 business days. I'm not really sure what the difference is here, but let's do this one. All right, and then you just click Save to Cart. You agree to terms, And here you're going to upload your Gerber files. So you make sure that you have clicked that it's in Gerber file format. You click Add Gerber file, and you locate your zip file and upload. And then you just click Submit the file now. And now this file will go to their engineers, and they're going to look it through and make sure everything is okay. If they have any questions, in my case, they asked me to verify that I wanted 2 layers. And if they do the same for you, just say yes, only 2 layers. So then you just wait until they have checked it. It takes, I don't know, a business day or something. And then you can complete the payment and the order. All right, pretty nice. It's going to be very fun to get this thing and assemble it. So that's it. There is one more step, though, not with regard to the electronics, but I want to create a case around the circuit board. So this becomes really professional, and then I can 3D print the case. So that's what we're going to do after the break. Alright, so now we're going to create a case. And before we go into the Blender, we're going to export this board into Blender so we can use it for measurements. So what we do is we hit export in the menu. Need to go into the PCB editor, and then we export and we select. Right, this time it's going to work because I have tried this process before, but I tried different options this time, and you should never do that, right? So import from X3D, skeleton key, file unit should be millimeters, import, and now we wait a little bit and we get all of these different things right here. So what we need to do is we need to select all of them. There we go. And then we call this the board. And let's go to the settings and make sure that we are using millimeters. And we click units and we change this length to millimeters. And if we scroll, this is our board in a 3D model. Pretty cool, huh? But we want it to lie flat on the Z-axis. So if we click and we go to the rotation, so we want it to be along this axis, and we want it to be minus 90 degree. Is this right now? In the middle, like so. Kind of cool that it got all of this detail. I mean Shift A, and we create a mesh and let's start with a plane, and let's not make this so huge, a little bigger than our board. And let's make this transparent, at least temporarily. So we need to go into the object, visibility. Let's see where we have this. There are so many options, right? Relations. Display. Not here. Physics. Let's see where we have it. Maybe it's up on this little arrow here. I saw this just the other day. Well, let's do this instead. Let's select this, press tab to get into the settings, and you can do this to make them a little bit easier to handle. And then you press X and you select to delete only the faces. So now we only have the frame here around it. And now we want to reposition this so it just about fits our board. We have to make no, never mind that. We are gonna make this thicker later on, but on the outside, not on the inside. So we can make this pretty tight around it. And how do we do that? Well, the easiest way, I think, is if we go up here and we select edge select, we hold down option and we click on the edge, which will select everything like this, and then we have the scale, so we can scale along this axis and along this. We can zoom in a little bit. And a little bit more on this. And it can be good to use, let's see, what did I do now? Okay, so this is from the top. Let's do something like this, and then we need to move it a little bit. Try to center it pretty good. And then move it just a hair. Scale it up one step. Something like this, I would say. So it's just around it. And on this side, we get it like this. Okay, sounds good. But I think we need to, if we press tab and we select this, and we see this from the Y view, they are in different positions here. So let's move this up. Something like this. And let's check the X view. Looks right. And the Z view was okay as well. So now we have it just around it like this. And some components are sticking through like this, so we need to give it a little bit of height. Okay, that's nice. So now we want to extrude this. So let's click on this and tab, and then we can press A to select all edges, and we want to extrude by pressing E and then Z. So we extrude it along the Z axis. And how big should we make this? maybe we could do, if we undo this, do you remember the thing we did in Blender the last time? Let's import let's see, how do we import this? Didn't get anything. Or maybe we need to be in this view. Import, and we take, maybe it was another format. STL, this I think. Ah, there it is. So let's check this from the Y view. And let's move this up a little bit. So this should be around this height, I think. Let's check it along the X and the Z. So this should be at this position right here. So this is our key switch, or at least the general shape of it. Right. So now we know a little bit about the height, right? Because we want it to go around here. So let's save. Let's select this one, hit tab. We extrude along the Z. And we make this, let's hold down control. Can we do that? No, we can't. Maybe it's better to see this from the, let's undo. And we'll look at this through the Y axis. And we extrude along the Z, and we go right about here, like so. All right, this looks pretty good, right? And we need to cut a hole for this. And also some kind of hole so we can get to this power thing here and have our power button. But before we do all that, let's go back into this object view. And we need to add a modifier because we need to have some thickness to this. So we go to modifiers, make sure that we need a better name for this. Let's call this the base. And add modifier, generate, and this should be solidify. And let's make this 2 millimeter, and we want the offset to be 1, which means that it grows on the outside. Okay, looks pretty good. Maybe we can round off the corners a little bit. So click here and tab, and we can select. Let's see what happens if we go to face select, select all, and we hit bevel. And we don't need to do much. So maybe something like this. And then we want to increase the number of segments, making it a little softer. Yeah, something like this, just so it's not very sharp. And we can actually take some of these. So if we go to edge select, we can actually do the same here. Let's not do all. Let's select the edges on the bottom to begin with. So we hold on this function, and we select, deselect, and we select this. We bevel. Okay, it didn't work. Never mind. But we do need a bottom plate as well. So make sure you have this whole thing selected and you press F. And then we get the bottom plate. And the bottom plate will also have the same thickness as the rest because of the modifier. Okay, so that's that. Next step is we need to cut holes for this port right here. And in order to do that, we need to create a small block which decides how big this hole should be. So if we go out from this mode and we do Shift A and we select a cube, and let's not make it so big. Let's try to position it a little bit. So let's go to the Y and try to put it in the middle like this. And we scale and make it just a tiny so. And let's move it like this, because this will drill a hole into this thing, and we need to position it so we find the port. We can make the base invisible. We go to the Z view, and scale, so we can press Control and make it something like this. Let's position it as center as possible. Let's just double check it from other directions. Here we also need to scale it. So let's see, we need to cover the whole of this. And something like this, I say. So we move, position it something like this, and we can put the base visible again. Yeah, I think this is going to work. So how do we use this block to drill a hole? Well, let's name it first. So this is our serial port. And what we do is we unselect and we select the walls. Maybe we can call this walls instead. And this solidify modifier we can let be for now. So click this arrow and we create another modifier, generate boolean, and we make sure it's set to difference, and we want the object to be the serial port, like so. And now if we make our serial port invisible, we have a hole. Would you look at that? And I think it's just about right, don't you? It's a little bit too big on the height, possibly. But we can arrange that. But we should be in object mode and scale. Let's see here. Maybe something like this. No, that's not big enough. I think this will do. So hit save. Okay. So that's nice. And we need to make some kind of hole for the power cable. How can we do that in a good enough kind of way? And isn't it a little bit too tight to these right here? If we select this and we scale it a little bit in this direction, let's see it exactly from the top. I think this is better. Did this affect our hole? Slightly. So let's take this and just move it a tiny hair in this direction. And let's see this from the X. Wrong direction. It's hard to get this perfect. Maybe we can do this in wireframe mode. Will that help? Not really. I'm not entirely satisfied with this, but let's not put too much time into this. Maybe we can scale this up. I mean down. Not that much. this looks right. Alright, so save. Okay, so that's that. And then we need the power as well. So I want to be able to put a cable here and either connect to this or to this. So I'm thinking about just cutting a small strip through here. For the cable. It's good for ventilation as well. So let's create another cube. And this we can scale so it covers the entire thing here. And it should be fairly not very wide. So let's see. And let's check it from above. So where do we want it? Okay, it's on this side. So maybe just here. Let's see how it looks. But let's move it up so we are not messing. Let's do 2 millimeters. Now we are exactly at the bottom. So let's see, I think we can do Shift A. No? Is it Command A? Yeah, apply. Location, I think. So now if we try to move this thing and we select 2 millimeters, we get it just right. Good. So this is how I want it. And let's call this the strip. Power strip. And as before, we go into this object, the walls, and we can create another boolean. Set the difference, we select the power strip. And we make this invisible. No, not this. we make the power strip invisible. Okay, so now we have a little hole right here that we can put the cable through. All right, so now we have taken care of all of these ports. So what else is there? Well, when we create the top of this thing, we need to cut holes for this key, because this is going to be on the outside. And we also need to make sure we have for these holes right here, which should go through everything, and including the top. And these LEDs we also need to take care of somehow, so we can see through the colors. Alright, so I think it's time to create the top. So let's see how we want to do this. Let's take these walls, make a copy. Now we've made copies of all of these as well. Let's Control C this, and let's go into all of these modifiers, except the solidifies. We take two booleans and we hit apply, and now we can delete the serial port and the power strip, and we will still have the holes. So now if we copy this and paste, and we swoosh over, let me just check one thing. If we swoosh this in this direction and we set this to 0, no. So let's Control C so it gets back here. Let's make the regular walls invisible, and we take these walls and we hit Command A, location, and now we swoosh it over, and if we move it in this direction and we set this back to 0, why is it? Well, never mind. It doesn't matter. So let's see here. What do we want to do? We want to go into edit mode and into edge select, and we select this top edge here, and we press F so we create a face. And now we need to cut off this thing. So let's create a plane. Push this over and make sure it covers everything. Let's go to the X, and this should be 1 millimeter from the top. So let's see, let's try to align it. Like this, and now we can apply the location. And then we move it down a little bit, and we set this to -2. And now it has the exact right thing. So let's see, Y and Z. Am I at the wrong object now? Let's Control C. Let's make these walls invisible so we don't mix them up. We take the plane and try to align it. Seems just about right, I think. So with the plane selected, Command A, location, and with the plane selected, okay. And now we want to move this thing. -2 millimeters. Okay, that looks good. So let's go into this and we create another boolean, difference, plane, it did not get much left. Let's Control Z this. And before we do this, let's apply the solidify. And now we try again. maybe we need to pull it down just a hair more. Something like this. Well, I think this is actually going to work out. So let's apply this and let's delete the plane, and this is our top. We go into edit mode, select all, and we do we do X, select, delete only faces. So let's see. Why does it become so weird? Let's see if we can delete all this stuff. We clean out all this stuff. And this frame right here, is this the right size? So if we put our walls back, no, this looks more like it's about the size of the plane we had. Yeah. I think we need to start over actually. So let's take this, copy, paste. Move this over. We apply this modifier. So what do we want to do here? We want to create a face on top of it. So we go into edit mode. We do edge select. It's probably because of this hole right here. Can we connect these vertices? If we go into vertex select and we select this and this, and we join them. And same with this. By the way, press J to join. And then I guess we can delete this vertex. No, we can't. Okay, what will happen now if we try to select the edge here? I wonder if we can remove that hole. We can Control Z all that way back. Alright, let's do it another way. Let's just create a plane with the same size as this thing. So if we look from above, that's the z-axis. And we create a new plane. And we try to scale it manually. Something like this. And this. And it goes a little bit outside, but is that really a problem? Let's see if we can scale it one step. I think this is going to work. Okay, that looks good. So this is our top. And let's make the other ones invisible. And we go into edit mode. We select all edges, delete only faces. Select this right here. We extrude around the z-axis, and we want this to be 2 millimeters. Like so. We go into edge select and we create a face. So let's see. We want this to be solid. Can we, if we go into face select and select this, can we extrude this around the z-axis? Around the z-axis. Yeah, we can. So let's make this -2. And now we have it solid. Let's go back a little bit. So we extrude this along the z-axis, but we set it to 0, and then we add a solidify modifier, 2 mils and 1. Maybe we cannot have it to be 0. Extrude along the Z, and let's say 0.1 millimeter, and now we solidify. Ah, there we go. This looks right. Nice. Okay, so let's see here. Where is the rest? Let's move it in position. Something like this. We can scale it a little bit because it doesn't need to be this much bigger. And let's check the Y. Same here. Alright, something like this. We save and we take the walls and make them invisible. And on this side we wanna go into edit mode and we want to inset face. Bugged out. So face select, we select this. Why is it not possible to select this thing? There we go. But we want to select the bottom face, and which one is that? It's here. So this is the face we want to select. And we want to insert face. Maybe we need to apply, that's probably it. So let's apply the solidify. We need to go back into here. So solidify, we apply. Now we go into edit mode. And face select. This is the right thing. And we want this to be, let's see, 2 millimeters as well. It's a weird angle, but this is basically how it is. So we just create a face on the bottom here, because what we can do with this face is we can extrude this. So if we do E and Z, we can do this. So let's say another 2 millimeters or minus 2 millimeters. So now we have an inner thing right here, but this did not look right. So we extrude Alright, nice. So now this will fit on top of our thing and be into place, so to speak. Alright. So let's put all of the other stuff back. And as you can see, it works out nicely. The thickness though here is 2 millimeters. So maybe we are a little bit tight. How can we fix that? If we go into edit mode and edge select, and we select the edges around. Something like this. And let's shrink it a little bit. So move this ring right here. But that's not it either. Maybe we need to do an edge selection of this instead. And this, and this, and move them. Or scale them. Okay, this is more like it, I think. Does this look good? Or did we do this too much? Yes, we did. There, I think. And how does it look in the regular view? Yeah, I think this is good, right? So this will be into place. Okay, cool. So what else? We need to drill some holes. For this. But I think we can cheat a little bit if we, let's see, if we take this, we make a copy, and we scale this up just a hair. Needs to be in the right one here. Let's do something like this. I think we can use this to drill a hole. So we select our top, add a boolean difference, we select our R&D number 1, and we apply. Now we can delete the R&D 1, and we have a hole. Okay. Yeah, looks nice. Okay, so now there's not much left. We have taken care of almost everything. It's just 2 things. First, we need to make these screw holes right here. So let's make a cylinder. Cylinder, radius, I don't know, 20. Let's try to position this. Let's make this really round, so 128 vertices. Let's scale this down. So let's see. So we need these holes to be at least as big. Something like this. needs to go through every layer, so let's make them really long like this. Right. And maybe we can cheat a little bit by creating an array of this thing. We need to have an offset. Why does it look so weird? Okay, something like this. And then we can create an additional array. Only this time we don't go anywhere in this direction, but we go in this. Alright. So let's apply. Let's call these screws. And these needs to go through every layer basically. So we need to add a modifier for each and every one of them. So let's start with the board, add modifier, boolean, and it should be the screws. Can we copy this? No. All right. And then the R&D we don't have to care about. The top we need to add screws, and the walls we need to add because the bottom plate is also part of the walls. So we add it here as well, link it to the same object. So if we make the screws invisible now, we have holes all the way through. Nice. So apply, and apply, and apply. And apply. And now we can take the screws and delete. But what's that? That's a bit weird. Doesn't matter. We're not gonna have the board produced from this sketch anyway, so we don't need to care about that. Okay, very nice. So what else? I said there were two things left, the screws and something else. Right, in order to conserve a little bit of material, we should make some ventilation holes. At least on the top and bottom, and maybe one of the sides. Can we do all of that in one go? No. But we can use the array modifier, and this is the last thing we're gonna do. So, alright, we do the same thing, but this time we create a cube, and we pick a direction. Well, I don't know, something like this. Let's check the other directions. This should just go through. No, it should go through all the way. Alright, so let's call this ventilation, vent, top, bottom. Okay, so add modifier, generate an array. Let's see how many we should have. Should not go in the X, but it should go this way, but minus this way. Maybe minus 1.5. 3. Let's do -2, 5. And how many? Something like this, perhaps. I think that's okay. So we go to the top, Boolean, ventilation, apply. We go to the walls, and this will also reduce the material and the printing time. So it's a win-win-win. And apply, and now we can delete this. And this is how it looks. So now we have some nice ventilation. Kinda cool, right? And same, we don't need to do the side if we have both top and bottom, right? Plus it's a little bit cool that it's transparent, I think. Oh, I forgot one thing, didn't I? I wanted these LEDs as well. So how does that work out with these? Actually, it's going to shine through here. So I think I'm okay with that. We need to be finished somehow. We can put how many hours? We can put millions of hours into this. But sometime we need to call it quits, right? And I think that's where we are now. So this is what we have built. Kinda cool, huh? Alright, so we're not gonna use everything here. So this should, maybe we can make a copy. Like so. And now we can delete this, and we can delete the board. And let's add some materials as well. So this top, we go to the material, new material. Let's call this top material. Alright, so on the top here I want to have some grayish titanium or something. Maybe something like this. And I want the roughness to be quite big. And it should be 100% metallic. light temporarily. Light. Kind of hard to see this fast render mode, but I think I want to make it a little bit darker. Okay. And this I want to have some more chromium kind of thing. So this is the walls material. So here I don't want as much roughness. And I want to have some kind of off-white. Should be metallic though. Well, something like this. Where did that light go? Yeah, something like that. It's not an exact science. Okay, ladies and gentlemen, we are done. So now all we need to do is we take this top let's see, and we rotate it like so. And we swoosh it over. something like this. It doesn't have to be perfect in this sense. Okay, our case is done. Let's save. And we need to export this so we can delete this point light. We select these, we save, we export into STL, selection only, and this is the case. Alright, so now we can just send this to our machine, or if we have one, or we can go to PCBWay because they do 3D printing as well. So you just go to CNC and 3D printing, and you just upload your file, STL file, this one. No, not that. What did we call it? Ah, this case. Here we have it. Sorry, my cat is crazy. I just need one. Design units, millimeters, material. I want titanium. The titanium is probably gonna be pretty expensive, but well. So let's see, color, metallic, surface finish, discrepancy. No. I'm not sure what to pick here. Others. Computer device. I guess that's it. Submit request, agree, and there we go. Alright, I really hope you liked this episode. Don't forget to subscribe, because in the next thing when I get this produced, I'm gonna code the software and make it work, and solder everything. So thanks for watching. Thanks for today. Alright, you guys, welcome back. So now I am done with the outputs, and as you can see, each of them goes to this resistor to ground. So this is a default setting, a logical 0, and then it goes on here. So this connection goes to the output module that we're going to do later on, and all of these have the same structure, and then we have all the labels here, and on this one we have the enable bar, so the inverted enable signal, which comes from here. So that's pretty much it, I think. Have we connected everything? I think we have. Alright, we are starting to see the end of the schematics part. Right, so now we only have the output module left, which is the simplest one in one sense. So we do only have one chip, but that chip has more connections than this one. So let's see here what we get. So if we make this a little bit smaller on this edge, we can make it a little bit bigger here instead. And let's see here. Let's move both of these down just a hair. So how do we want to do with these labels here? Is it better if we center this? I'm not sure. Well, maybe. Or we can put it on the left corner instead. That's actually much better. Alright, this looks real nice, I think. Pretty nice, pretty nice. Alright, so let's see here. Now we will take care of the output module. And so let's see here. If we go to my where did I put my stuff? Here. We're going to this is the name of the chip, the W65C51, and this is a UART chip. It's called an asynchronous communication interface adapter here, or ICIA, but that's their brand name. Well, what this is a UART chip. And what is a UART chip? Well, it's I'm going to show you how the chip looks. It's easier to explain here. So it has a lot of different inputs and outputs, but we're not going to use most of these. But here are the important ones. We have 8 of these inputs. So we connect these to our bits, transmitting the secret key. And this chip in turn is going to take these individual bits, turn them into a byte, and it's going to send this in serial through this transmit connection here. And why do we need a chip for this? Can't we just use like well, some kind of counter-like chip, which just turns a parallel connection into serial? Well, we could do that, but the problem here is that when we're communicating on a serial link, it needs to be at a certain speed, for example 9,600 bits per second. And it needs to send these bits at each exact clock tick in that speed. And that's what this chip takes care for us. So this is what we need to build, and we will start by doing like we did before, by creating the schematic symbol for this. So let's go back into KiCad and the symbol editor, and we go down to our library. We right click, new symbol, and this is going to be called the W65C51. Okay, so let's move this U away a little bit, maybe further. And we will start, just like before, with creating the first one manually. So the first one here is the VSS. So we will create a new pin, which we are going to call VSS. The pin number is 1. This is a, let's see, it's a power input, right? And let's do, no, let's start with this direction. Okay, so we put it right here. Right, so now we have 1. And now we will do what we did before. We will click on this table here, and we will create all the pins, and we have 28 of them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 11, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5, 6, 8. I think that's right. And now we will number all of them like this, and then we will just fill in the blanks. Alright, you guys, so something like this. We're going to change a few symbols. So this chip select 1 bar, this needs to be an inverted 1. So we'll change this to the inverted symbol like this. And these two are clock symbols. So we're going to change it to, let's see, well, they are inputs. Don't we have something for that? Well, we'll set it to input, and we'll change this to clock. And this too, I guess. And what else do we have here? CTS B. I'm not sure if the B is bar. I don't think so. And this is a transmit pin, so output. This is okay. This V2 is a output and a clock. And our Q is correct. All of these are correct. Yeah, so this is how it should look like. Pretty nice, huh? So let's close this down, go back to schematic editor, press A, search for W65C51. Let's rotate, and we'll put this somewhere in center like this. All right, that looks pretty nice, I think. So as usual, let's start by connecting the VSS and the VDD. So the VSS, that's the +5. and the VDD is the ground pin. Alright, so now we just need to connect these other pins, but a lot of these we are not going to use. So we need to tell the program that they are not going to be used. So to the right here we have this little symbol, place no connect flags. So we can click on this, and now we just click on all the pins that we are not going to use. So RESB, RX, so all the RX pins, because we are not going to receive anything, we're only going to transmit. The clock stuff we are going to use. CTSB, no. Transmit we are, but not this, not this. These we are going to use. And this, but not this. And not the IRQ. Data we are going to use, and not these two. Press escape. Alright, so this makes stuff a little bit easier, right? That we have some of them that we're not going to use. Alright, so sorry. So this chip select, these are what's activating this chip. So CS0 needs to be high and CS1 bar needs to be low. Then this chip is active. So let's begin in that end after the break. Alright, welcome back you guys. So before we continue with the output module, I want to make a small change, because I'm not really satisfied with how this control module looks with regards to this power LED here, because the electricity goes this way, and I don't like it's too complicated, too error prone. So let's do it a little bit differently. If we go over here to the input module, we can see that on the direction pin we connect it directly to 5 volts. Let's not. So let's delete this one. And let's instead drag this like so. And let's give this a label. So let's say that this is the did I choose the right one? Yeah. This is the power. Let's just call it power. And we click here. Alright. So then we can go over to the other module. And let's delete this connection. And let's move this up. Okay, so it goes from ground through this 1K current limiting resistor, and through this LED. So if we take this connection right here and we pick our power wire and connect it here, so now it's going to let's see, but but we need to change it a little bit. Right, we need to rotate this and connect this to +5. Okay, so now we go from plus here, through this resistor, through this LED, to this power line, and into this direction pin. So the direction pin will still get, well, not +5 volts, but enough volts to be on the on state. And this sketch becomes a little bit simpler. So let's see how this looks. So we go through this and over to ground. Maybe it's better. Let's see here. What if we were to, if we click on, if we press W to get the wire, and we connect it here, delete this one. So let's see, we want to get this. This should not be here. Okay, so now the current will flow through this thing and over here. And if this switch is on the off state, what is going to happen then? Then it will go, let's see here, right, then it will go like this, putting a logical 0 on this and a logical 1 here, exactly what we want. But what about this connection? Can this cause any problems? Power will go through here. No, because this will be disconnected if the switch is disconnected, which means there will not go any current here. By the way, shouldn't this be on the other direction? How do I rotate this on that axis? Let's see here. Mirror vertically. There we go. So now, if this is on the off state, no current will flow here because this will be inactivated, which means the only flow will be from this logical 0 here to ground. And nothing will flow here either because this can only take in one direction. But if this is on the on state, it will flow into this here, activate it, which will let the current flow through here and down here. Okay, this is better, less error prone. So let's see where we were. We are going to make the connections for the last chip. So what do we know here? We have the D0 to D7, and here we have B0 to B7, so these need to be connected. So let's do something like this. And then we need to assign the labels. So let's start with B0, rotate, and B0 will be connected to D0. And we'll keep this up. Connecting all of these inputs. And we have number 4 and 5, 6, and 7. And as you can see, we have almost connected all of the pins that should be connected, but we have some left. And let's start with this XLTI and XLT0, because this chip on its own cannot work as a clock, so to speak. It needs to be very accurate, the timing, which means that we need to have some external circuitry that tells this chip when to send the signals. So we can use a crystal. And a crystal works that way that if you put electricity through it, it's going to let that electricity through at specific intervals. So if we go to, no, not this, if we go to the datasheet and we scroll down quite a bit, it's going to show us how we can connect one of these crystals here. So either we have some external clock oscillator, which we will not have. So this left sketch is what we need. So this right here is a crystal. So we're going to connect it on both ends. And we're going to take 1 milliohm resistor and connect it in parallel like this. And then we're going to have a 30 picofarad what is called? C something. I always forget what that is called. Not a comparator. Let's see here. Capacitator. So here we need a 30 picofarad capacitator. So let's build this thing. So we're gonna start by grabbing one of our resistors. Let's put it in this direction, and this is going to be not 10K but 1 mega ohm. And if we unclick and we click on these labels here, we can put them on the sides. Alright, so let's align this like so. And we connect it to the input. We connect it and we click, and like this. And now we need a crystal, so we press A, we search for crystal, and we take the first one, rotate, no, not rotate, let's put it like this, escape, click here, and move it here, and double click. And instead of the value crystal, we're gonna say that this needs to be a 1.8 gigahertz. So it's going to send a signal 1.8 million times per second. And that's according to the datasheet. So this chip will take this input frequency and create 9,600 bits per second, or whatever we configure. And I'm going to show you how to configure it in a little bit. So let's connect both sides in parallel like this. And now we need a capacitor. Let's take this frame, give us some more room. So we press A, we search for C, we rotate, put it here, we can move the labels, and this is going to be a 30 picofarads. Maybe we can put it on this side. And let's see how we're going to connect this. So one side should go to the XTLI, and one side should be directly connected to ground. And it doesn't matter which way. Like this. So now we have the clock circuitry. Alright, it's not many left. The next step is this chip select. So in order for this chip to be activated, we are gonna need a positive signal on this CS0, and on the CS1 bar we're gonna have a negative signal. Which means we can just take this, connect, we take the +5, and we connect, because we want this chip to be activated even if the key is turned off. And why is that? Well, let me just move. Okay, that's better. Because when this chip is not activated, we are going to configure it. And when it is activated, we are going to send the data. And what will control what is this RS0 and RS1, the register select. So let's see how this works. If we look at the data sheet, not the status register, control register. So this is where we select the rate. So basically what we do is, let me just check. Talks about the register select here. The two register select lines are normally connected to blah blah blah. But if we look here, if both are low, that means that we are going to we're going to transmit data. So if register select both are low, we're going to transmit. So this is when our key is in the on state. But if both are high, we write to the control register instead of sending the data on the wire. Which means that both of these register selects, we need to be the inverted version of the key. So if key is on, this should be off, and vice versa. And how do we achieve that? Well, we have already achieved that because we have this signal right here, enable bar, which does exactly that. When this is on, this is off, and vice versa. So we only need to connect that as well, but we connect it to both of these register selects. So let's do something like we connect here like this. We press W and we draw an additional wire. Bar onto here. Alright, so what will be the configure values? Then we need to scroll up a little bit so we see this command register here. And here are the 8 inputs. So these correspond to these right here. So we're not going to use parity, so we don't need any of these. Oh. And we don't need to do any echo. We don't have to care about interrupts, which means we don't have to care about this. The only thing we need to care about, let's see here. We'll not just stop bits. The word length should be 8 bits per byte. So this should just be 0. This should be 0. Receiver clock source. Receiver clock source. We don't have to care about this because we're not going to receive anything. So this should also be 0. But here we need to be careful, because we need to select a speed that we can deal with. So 9600 is easy to use, which means that the bits 0 through 3 should be 0, 1, 1, 1. Which means we need to alter our default state for the inputs, because you remember this view right here. All of these are connected through a 10K resistor to ground, which means that all of these are 0 by default. But we don't want them to be 0. We want B1 to be 0, but B2, B3, B4 should be they should be +5. So let's put this here, remove the label, copy, paste, copy. No, we're on the wrong side, right? No, this is correct. And don't forget to connect them. Alright, so if this chip is not enabled, so if the key is not turned on the on state, these are going to default to 0, 1, 1, 1, 0, 0, 0, 0. Otherwise, it's going to send through our secret key. So a 0, 1, 1, 1 means that we have the number 14. So we need to, when we configure our software, we need to check if it's 14, we should not do anything. And if it's any other thing, then we should treat it as a command. Okay, we are starting to get close to the finish line here. Let's see. Okay, this read-write pin we need to deal with as well. So let's go to the datasheet and see what that is used for. So the read-write input generated blah 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 blah. A high on the RWB pin allows the processor to read the data supplied by the ACIA. And the processor in this case is, well, we don't have a processor, but we are not going to read from it. We are always going to want to write to it. So a low allows a write. So it should be connected to ground. Like so. And then we have the reset pin, which I forgot earlier. So a low on the reset input causes a hardware reset to occur. So we need to pull this high. And where is that? It's this res B. So we need to zoom in here, click on this cross and delete it. And let's do something like this. If we select both of these, we move them down a little bit. Then we can copy the symbol. connected to the reset pin. Okay, I think we have connected everything. Yes, we have. So this is our schematic. Quite nice, huh? Pretty professional looking, if you ask me. Okay, so that's that. Our next step is we're going to prepare a small 3D thing, because if we go to the datasheet for the key switch, this thing right here, it doesn't exist as a footprint in the KiCad database. So we need to produce a footprint which is basically just the size and the pins, and we need to create a 3D structure for this. And it doesn't need to be very complicated, we just need the basic shape. So in order to do that, we need to download a program which is called Blender. And it's a rather complicated program, but we are only going to use very, very simple features. So if we go to Google, we search for Blender. It's free software and one of the best 3D softwares. And we click download and we install the thing. Then we're going to use it just in a bit, but first we're going to create the footprint. So we go to KiCad, go to the footprint editor, this right here. Let me just resize it a little bit. All right. So let's see, it became very small. Can I remove this properties somehow? I can change this. Let me see if I can remove that. Panels, properties. There we go. Now we have some room. Okay, so we need to create a database here. So we go to, first we go to the preferences, the settings, and we go to the footprint editor and we make sure that full window crosshairs is enabled here as well. So we need to enable it for every part of the program. Then we go to the menu outside of screen and choose new library for the project. And I will call this footprints. Then we go down to the footprints, right click, new footprint. And we need to give this a name, so let's see what this key switch is called. Here, 210.00802. So double click here. name footprint. So this is an R&D 210.0082. Was that it? 802. Okay. Click this ref and rotate it so it's in the right way. Let's zoom out a little bit and move this away for now, so it's not in our way. Okay. So we need to be a little bit accurate here. With according to its size. So this right here is the interesting thing. And it's a little bit annoying because it doesn't say what units we're in. But this is probably millimeters, right? I think it is. So this is from above, and the footprint is from above. So this is what we need to create. So basically, we can make a circle here, which should be, it should have a diameter of 15 millimeters. So we go here, we select a circle, and we need to set the grid to millimeters. It seems to be at the default setting. So let's click here on the origin, and we make sure the radius, how much did I say? 15. Which means the radius should be 7.5, right? Okay, so we need to do half millimeters. Actually, it doesn't cause any problems if we make it a little bit bigger. The important thing is to not make it smaller. So let's do a radius of 8, like so. And this is just an image printed on the circuit board. If we press Alt or Option 3, I think we will be able to come to this view right here. So as we can see, it's generating a circle. But we need to recreate this into a border, so it tells the program that we cannot put any other parts on top here. So if we right click and let's create from selection, and we need to create a rule area. And we need to keep out footprints. Okay, so now it turns into these lines here, and that tells us that this is a rule area, which tells that we can't put anything else here. But this rule area is not visible, so if we go to this view, it has disappeared. So what we can do is we can right click on it, and we go to create from selection, and we want to create lines from selection, and we don't want to delete the object after conversion. So now we have both lines and one of these. So now the circle is back. Okay, so the other thing we need to add is the two pads. Because as we can see here, we have these two connectors on the bottom. And they should be 4 millimeters apart, and they should be evenly distributed from the center. So we click on this pad icon here. Let's go to the center, and the grid is on millimeters, so this will be so if we have it 3 steps, no, 2 steps from the middle, we go to the middle and we go 1, 2, and we can double check if this is correct by using this ruler here. So click that and click in the middle of this and go down to the middle of this, and as you can see there's 4 millimeters apart, which is good. And let's also edit the pad type. We're not going to use these SMD service mounted, we're going to use through hole. And the hole shape should be round. And how big is this going to be? It doesn't really say, does it? Which is kind of annoying. But it doesn't matter if we make it too big, as long as we don't make it too small. And it almost seems like there is that this is as wide as this, or at least half of it. So somewhere around 3 millimeters diameter should be fine. Let's see. It complains that it does not. We need to change the pad size as well. So let's make this X and Y. Let's see what happens if we make this 4. It's rather big. Let's see how this turns out. Through hole and 3 millimeter hole. I don't like that these connect. Let's make it slightly smaller. So let's say 3.9. So this is not an exact science, but this is going to work. The important thing is that we can connect our cables or connectors. And if we go to the live view, we can see that this is how it's going to look, which is great. So let's take these reference things . this here, and this we can put here. And here. Alright, something like this. It's not perfect, but it is going to work. But this is only a 2D thing, right? What's going to be printed on the circuit board. But we're also going to need to have the Z-axis. So that's what we need to create in Blender. And let's save this, and we will be right back after this. Alright, you guys, so this is Blender, and you can move around by pressing down the scroll wheel, and you can zoom in and out, and if you have shift and use the middle mouse button, you will strafe around like this. So let's see here. The first thing we're gonna do is we're gonna select everything and delete, and we're gonna go to units, and if you don't see this, you click on this little drip icon, and I hope it's not too small for your screen, but you can always zoom in, because I can't really work with this program with a smaller resolution. So change the length to millimeters. Alright, so let's check the datasheet. So I'm not going to do it exactly like this. I'm just going to have the basic shape, so we have something to work with inside of KiCad. But this is the interesting part. We're going to start with a circle which has a diameter of 15 millimeters, which means a radius of 7.5. So let's start there. We press Shift A and select a new mesh, and we want to have a circle. And then you click this little add circle thing here, and you select that it should be 128 vertices, so it's round and nice, and that the radius should be 7.5, and then you just click. And then you can scroll in and press the Z so you see it from above. Alright, so this is what we've got. And let's see the next step. What is the length of this thing? So we are interested in this part right here, aren't we? Let's see. Yeah. So 25.5 on the Z-axis. So we can do like this, and you select this and you press tab, and then you get to this edit view with more icons here. I usually do this, so it's a little bit easier to see. And then you can press E for extrude, and then you press Z to extrude on the Z-axis. And then you just click anywhere, basically. Because then you can go into this field right here and specify exactly how much it should be, which is 25.5. So now we have this cylinder, and if we select up here this edge select mode, or we can press 2 on the not the numpad but the other one, and scroll in a little bit so you see that the edge here, and then you hold down option, I think it's Alt on PC, and you click on this little edge so this gets selected, and you press F so you get one of these faces right here. And you can do the same thing on this end. So we do this and F, and now we have cylinder. Okay, good. So what's next? I'm thinking that we should add this ring right here, because that is going to decide the top of our case later on. So let's see, how big is this thing? How can we see that? A little bit annoying that it doesn't say, right? Do we need to eyeball this thing? Because we don't have to get it exactly right, but it should be pretty similar. So let's see here how we can do this. I think the easiest way is if we go back into object view by pressing tab, we select this and we copy and we paste. So this is our second one. And let's rename this. So this is the ring and this is the base, let's say. So we take this base and we remove this eye here, so we only see the other one. And then we can click here and we can use our scale. And we want to scale this along this blue axis here. And we can hold down Control, so we do it in steps of millimeters. And make it so. So now I think it's 1 millimeter. Yeah. No. Let's see. 3 millimeters. Let's make it at least 2. So something like this. And we can, if you get so you have this resize thing here, you can push it all the way and it will disappear. Alright, and we need to scale it so it's a little bit bigger on the other sides. So let's see how we can do that. And take this ring right here and just make it a little bit bigger, like so. So if we take this base back, we can take this and select move and move it on this axis. So we have something which looks, let's check the datasheet. Maybe something like this. And we want to merge these together. So we do that by clicking on the base and we go to the modifiers. We click add modifier, and we want to have a generate and a boolean modifier. And we want to union this with the object ring, like so. And then we click this little arrow and we click apply. And now I think we should be able to delete the original ring. Yeah. So now this is one structure. Okay. Let's add the connectors. So as we can see, we have these two connectors which looks like this. But I'm just gonna make it like a square, and it should be 4 millimeters between them, evenly distributed from the center. Alright, and it looks like they are about the same length as well, maybe 5 millimeters. So we can hide this, and we press Shift A, and we create a plane. And this plane, what did I say? 5 millimeters. Go to the scale, and we scale it along this axis with control. Something like this. So now it's 5 times 0.5, maybe 1 millimeter. Something like this. And let's give it some thickness as well. So we click, we press tab, we choose to extrude by pressing E along the Z axis, and let's make this 0.5. So this can be our connector. So we can call this con1, Control C, Control V. We need to go out from this mode with tab. Control C, Control V, and this is our connector 2. So, and let's select both of these, and we choose rotate, and we want to rotate these along the this axis. And we want to make sure that we rotate it 90 degrees, right? Something like this. And if we get the base back, we can select these two and move them up quite a bit. And then we put this back, can move them down, maybe put them under here. And now we want to put them in the right place. So now currently they are exactly in the middle. So let's grab one of these and let's choose the move, and we want to move it along here. So why doesn't it snap like it did before? Never mind, let's just move it tiny bit like this, and we change the Y position to 2 millimeters, and we take the other one, move it a little bit, and set this to -2. There we have the 2 connectors. Select them both, move them down, something like this, and we want to merge these two. So we select both of them and press Command J, and now they're just one connector. They are one object, and we do like we did before. We go into this one, add a modifier, generate boolean union, and we select the cont, and we apply, and then we can delete this cont. Okay, so this is our basic shape. Right. Looks pretty nice, I think. Alright, so let's save. And I'm gonna put this inside of here. I'm gonna call this the R&D 210. That's the name of the thing. Save. And now we need to export it to the correct file type. So we go to File and Export, and what we are interested in is X3D extensible. If you don't have this, you need to add one thing. So let's see where I did that. You go to Edit and Preferences and get Extension, and you search for X3D, and then you install this Web 3D thing here. And now you can go to File and Export an X3D extensible. So let's see here. Yeah, I think we can keep everything as is. So export this, assign footprints. And this doesn't really fit on screen, but we'll have to make do. Alright, so here are all our components. And for each unique one of these, we need to select the exact footprint to use. And one of them is easy, that's a key switch, because we have our own for that. So if we go down to the library, or what did we call it? Footprint here. So if we click footprint, here is the one. So we double click, and now we have selected that. But we need to select for the rest of these as well. So we can take all of these resistors and do them at once like this by shift clicking. And what we're interested in are the resistors. and we want through-hole technology. Alright, so let's see here which one we want. And here you should really select the ones that you have in your workshop. So I'm just going to use, let's see, horizontal. Yeah, I'm gonna use this one, I think. And can we check view selected? And we do all three. Yeah, this is a regular sized one. But the important thing is that we have these through holes, because it will be very difficult to solder otherwise. Okay, so that's all the resistors. Then we need to do the capacitor. So capacitor through hole technology. Let's see what we have here. I wonder. Let's try this one and see how it looks. That's not the kind I like. Let's double check this. No. The best way to do this is actually to go into one of these websites who sells these things and find the one that you bought, and you just check the millimeters and all of other fields. This one I think is right. Disk, yeah, that sounds right. Yeah, this is the one. Alright, good. What else do we have? Unlock and power. Okay, these are regular LEDs. So LED through hole, and I want to have quite the big one. And horizontal. Yeah. Maybe this. Okay, horizontal was not correct. So I guess the ones that doesn't say horizontal needs to be vertical, right? weird looking thing. This one sounds right. Yeah, I like this one. Okay, and then we need the transistor, which is through hole, no, transistor, not transformer. So transistor power. What is that? Should it be transformer? That sounds very weird. No. Transistor power. If it's not under transistor, what could it be? If we add and we search for NPN, bipolar transistor, SIM device, NPN, SIM type, gammelpoon. What can it be under? Very weird. Transistor power. Package TOSOT. This looks more like it. So package TOSOT. Could have never found to look there, right? So package TO, this one. And I guess this one. Yeah, this is more like it. Okay, what's left? We have the 74LS04. So this should be a regular chip. So let's see. So package zip, I guess. Or dip rather. So we have a lot of stuff here. So what we can do is we can search, and what we are interested in is, let's check the data sheet for this thing. If I have it. Not easily available. Let's do a quick search. So it's the 74LS04 datasheet PDF. So we have 14 inputs, or 14 pins. So if we just search for 14 here, we can choose one of these dip 14s. So this one, and if we view this footprint, it looks just about right. Okay, and then we have two other here, and I didn't name these. Let's do that so we don't mistake us. So if we double click this, and this is a 74LS245. This is the W65C51. Okay, and this did not update. Save. Let's go back into the schematic editor and let's choose the sign footprints. Okay, so now we see the names. So let's start with the 74LS245 because that's a standard thing. So package dip, and we search for, if we remember how big this is, think, let's not guess. Where is it? This. Alright, so we have 20 pins. So let's search for 20. And we select the dip 20. And let's double check. Yeah, that's perfect. Okay, so two left. We have the UART chip and we have the crystal. Let's start with the crystal. CR. Maybe this one. Yeah, looks right. Okay, so the W65C51, there is no footprint, and no chip is good enough to choose in the list either, because if we were to go to the dips like we did previously, so package dip, and this one has 28 pins, I think. Yes, but the problem is this is too fat, this chip. It's much wider than, because there we can find a 28 right here, but it's not wide enough. Well, we have the 15 mils right here. Maybe that could work. Yeah, this looks exactly right, actually. Huh, that's pretty nice. That saves us a lot of trouble, because now we have chosen footprint for everything. So we press OK, save, and now all of this is done. So the only thing left is creating the PCB, the actual printed circuit board, and then we are done. Pretty nice, pretty nice. Alright, so that's what we'll do right after this.